Okay, please enable your webcam so we can start, continue with our class. We will do a recap as usual for our previous class. We already go deep in our module 7 last time. Okay, in our module 7, it's quite interested module, especially we're going to deal with deadlock. So there will be things that can relate in terms of deadlock with our computer system and also deadlock in our daily activities life. So we done also discussion and look into what the example on deadlock for our daily activities on the traffic jam. So we know when we have where is the definition of deadlock? So deadlock happen, or might be definitions of deadlock, is that when a process, especially when we are dealing with the computer process, computer system, so it is related to process that you need to wait for other event. So if you need to wait for other event, that can be caused only another process, so it is going to be under a deadlock. So example, last time we take a look in our traffic jam. So last time we discussed that this lorry cannot move forward unless like this car move forward. So when this car move forward, then this lorry can move. So the event that can be, this is the event that can be caused for this lorry or a process to start or to be in another process in the set. Okay, so this is the things under deadlock. And we did cover also, what we covered last time is in terms of introduction of deadlock. We learn on what is the criteria under deadlock. And we also look into how deadlock will be occur. And we touch there will be a several solution or algorithm for us to solve the problem under deadlock, which is deadlock prevention, deadlock avoidance, detection, and recovery from deadlock. But we just last time touch a bit about the intro of deadlock preventations, but we not go deeper yet. We just see all the problem that occur. So please make sure you, before you go deeper, you already understand the introductions of the thing, especially when we need to have these three things: request, use, release. This is a normal process. Last time I already share with all of you. Before you go somewhere also, you need to have a request or permission, then you can use. Similar also, if you want to lend something from a friend, so you want to have a permission for you to use. And then after you use, then you said, okay, I already finished with this thing, so I will give back to my friend, or I just release the process. And in terms of resources, you take a look into the differentiation between two under physical and logical. And this is the important in terms of the error last time. How you're going to define whether it is a request or it is holding. So if it's pointing out from a process, it's going to be request the resource. So please take note that we will use only a short form of alphabet. P for process, R for resources. So all of this we did cover last time. So please remember back, we did this discuss about this last time. request age and assignment age. Only these two things. So I hope that you still remember, and it's quite easy. And there will be four for visualization, I guess so. A process we can use as a circle like that. On a resource, we can use a square or a box. And you can see also there is another square inside. So what is representations of this? It as a indistant. If you don't have, then you don't have any indistant. But if you have like one indistant, two indistant, you can draw it inside. So this is all the visualization that you can use to visualize your process. Another one is when you have a request instant. So you use a circle and also the square inside that is depend on your how many instant. It's not going to be fixed with 4. So if it's 3, then you draw 3 only. If 2, it's going to be 2. Okay. And P is a holding in distance, means that P or this process hold this resource. Okay, it on at that time, it's on these resources. Okay, type of age here. So type of age, you're going to have two. Just now we already looked into also request and assignment. So last time we discussed that it is easier for you to remember when you have a request, then you're going to point up to the resource. And when you point it back to yourself for the process, you can see here, it point up in yourself for process. So it's called as a whole, or this is your own resource. You own this resource. So just example, if it is pointing on and if it is pointing in. So that is the differentiation between request age and also assignment age. So this one is very important, okay? Then example of resources allocation. This thing you can see here, although it's not like a square, but you know, okay, this is in distance, isn't it? So if you were given with this visualization, how are you going to define? Okay, of course, this one is a process. When it's point out, it's said like a request. So you try to request the R1. But at the same time, why you cannot just tag this R1? Because you need to request and you need to wait. At the same time, it hold or it on by P2, process 2. And at the same time, P2 also requests for R3. So R3 is on by process 3. And there is another resources, but this resources is not dealing with anything, so you just ignore it. Another resources is on by P2 and P1. Why? Because it has two instances. Please remember that when you have two instances, that it can say that you can intend or on by two process. If you have 3, that you can on by 3. But if you have 1, you can only on by 1 and the rest need to wait or just to request. So the example also here been discussed in terms of RAG, a simple one. After this, you're going to go deeper also in RAG. And there is an important fact that you need to remember, especially how to define whether this example, this illustration are having a deadlock or not. So this fact, if the graph contain no cycle. So this is the very important, which is cycle. About cycle, then there is no deadlock. Like this example at 8, you don't have any cycle, which means that you did not have any correlation, you know cycle, right? So it is no deadlock because no need for you to wait. You can see here, this resource 1 on by process 1. This resource 2 on by process 2. So this process 2 and process 1 did not request any resource, any other resource. So no deadlock in between. Another basic fact here, if graph contain a cycle, so you can see here at B, if only one instant per resource start. So you can see last time, if you have, let's say in this resource, you have only one. Similar also with this resource. Then deadlock exists. Because you been request, here you can see, okay, it requests by P2. Okay, P2 requests the R1. But R1 on by P1. So you cannot entertain these two. When it requests, you cannot directly point up to this P2 because at the similar time, it's on by P1. Until P1 finish, then you can change and point like this. But before it's finished, it needs to be in a request or waiting. So if several instances per resource start, then there is a possibility. What about possibility? Possibility means that mungkin, maybe there will be a deadlock, maybe there is no. Although it's look like cycle like this, right? If you look like a cycle like this, but resource 1, let's say resource 1 having 2 instances. So you're going to point like this and you're going to point like this. So there is no deadlock here. So similar also, if you wrote resource 2, there is 2 instances, then you're going to have like this later on. Because it can entertain 2 process. There is no deadlock. So it depends also into us how many instances in the resources about the if you have a cycle. So you need to look into 2. But when there is no cycle, totally no deadlock. When you have cycle, you need to look into the instances. If only one, then totally no, then totally it is deadlock. But if it is having 2 or more instances, so you need to check for the possibilities. Okay, so that is a basic fact that you need to remember. So we already discussed all the example and how you're going to avoid the deadlock. If for this example, example 3. However, the system is not deadlocked when P4 release R2, this resource can be assigned for P3. So you can see here, this has 2 instances. If let's say P4 already finished, means that P4 release this R2. So these instances can be directly on by P3. So there will be no deadlock and so on. So please try to look back. This one we already discussed. And there is also another possibilities how you can also see when there is no deadlock. Now let's take a look in terms of the method of handling deadlock. We done already look into this diagram. For this diagram, you have several methods to handle deadlock. Wait, I need to silence this phone. Just now my student changed the setting. Okay. So method to handle deadlock. You have preventions, avoidance, detection, and recovery. Lastly, you will ignore it. Okay, in terms of avoidance, we have RAG, banker algorithm. In banker algorithm, you have safety algorithm and resource request algorithm. In detection, you also have RAG and deadlock detection algorithm. So, ensure that system will never enter deadlock state. How we're going to ensure it? So these two will be ensure you not to go for a deadlock state. Deadlock preventions, deadlock avoidance. You know this keyword already, then you know that okay, it is going to be never. Similar also in our daily life when we said avoid. If you avoid, then this thing not going to happen. Similar also, let's say, okay, don't go to let's say KFC. If you go to this KFC, then might be it will be happen something. So might be there is like 50-50. So for you to not going to go, like might be getting any chances, then avoid, don't go. So it's never going to happen any chances of percentage. Similar also in the preventions, going to prevent to go to KFC. So it is similar also in terms of our system. If you want to prevent, then preventions and also avoidance will be going to get never enter deadlock state. Well, there is another method for us to handling. Let's say you already accidentally go into the deadlock state. Then how after deadlock, how you going to recover? Similar when you go and then suddenly people already said to you, don't go to KL. If you go to KL today at 10 a.m., then you're going to start in traffic jam. So if you prevent, if you avoid, so you're not going to start in traffic jam. But let's say you say, I already in the middle of my way. So at 10 a.m. suddenly you are in the middle of traffic jam. How? You already done and already start in traffic jam. So you need to have a recovery from traffic jam. So your mentals, because you are tired already in traffic jam. So this one in terms of recovery. And if let's say you are a kind of very laid back person, you don't want to think about problem. So you just say, okay, if traffic jam lah, just face it. If let's say you have a problem with whatever things that you say, just face it. No need to worry, no need to headache. So it is the third option one, which is you're going to ignore the problem. And then you just saying that, okay, you pretend that deadlock never occur in your system. Okay, that is the things that we already look into in terms of the introduction. And in terms of a prevention, if fails any of these four conditions simultaneously arise during deadlock. So if fails any of these, so you need to look into these four. Mutual exclusion, hold and wait, no preemptions, and also circulation. In the conclusion, last time we did touch, mutual exclusion, only one process at one time can use a resource. This is the conclusion. If you want to use the mutual exclusion, you want to execute from your process. Hold on wait, process hold resource while waiting for others. no preemption. If a process has resource, it cannot be forced to give it up or cannot take a resource away from process. And lastly, secular waiting, the waiting process from a cycle. So let's take a look into this first thing under deadlock avoidance. So this is all under deadlock preventions, which is going to have these four. Last time we did take a look into this. And now we're going to look into the deadlock avoidance. This one is new for you. And you just learned it today. So how you're going to ensure that you're not going to do anything wrong in your life? Similar also, I don't want to go to do something bad. I don't want to face traffic jam. So it is a never. Means that I don't want to have any deadlock in my system. So what is a travel's way to avoid? Require the system to have some additional a priori information available on possible resources requests. So this might help you in terms of to avoid this deadlock. How? First one, simplest and most useful model require that each process declare maximum number of resource for each type that it may need. So let's say P1. So this process need to declare, okay, I think I need at least three maximum resource. So first, it need to declare. If P2 want to enter into your system, so it's need to declare, might be it's have maximum of two resources. So it need to declare maximum number of resource. Second one, the deadlock avoidance algorithm dynamically examine the resource allocation state to ensure that there is never be a circular waiting condition. So this algorithm, using a deadlock avoidance algorithm, can be dramatically, you always going to examine your resource allocation condition for you to ensure that it's not going to have a circular waiting condition. Circular, which means cycle on a waiting or request. And lastly, resource allocation state is defined by the number of availables and allocate resource and the maximum demand by process. So this maximum demand is already shows here, and you need to check always in terms of ability and allocate of your resource. Might be you're going to see, okay, resources now available 2 and allocation already gives 3. So you know, okay, maximum that can have in your P and etc. So it's going to be several. So later on, you're going to see in terms of bank loan structure, which is going to represent these whole things. So you're going to see, okay, this one will be covered. Okay, this is an example of deadlock avoidance. But actually, in deadlock avoidance, you see there is 2, right? Where is it? A banker algorithm or a rack. So let's take clue one by one. In terms of safe state, just now, in terms of state, how are you going to define that now your state of resources is safe? You don't know whether your resource enough or not for all the process that will be request. So you need to have a safe state for this resource. Sometimes the resource When it is not enough, that will be a cure awaiting, a request. So this will be a deadlock, a possibilities of deadlock, especially when it is in terms of a cycle. So system is in safe state if there is axis of sequence P1, P2, and etc. of all processes in system, just as for each PI, the resource that PI can request can be satisfied by currently available resource plus resource held by the PJ. So it might be confused for you to understand, but later on when you look into a real example in our daily life, then you can see. So that is if PI resource need are not immediately available, then PI can wait until a process J have finished executing. When they have finished execute, they can release all their resources, and then PI can obtain the need of resource, execute, return back the resource, as long as the cycle of waiting is not occur. When PI terminate, then PI plus 1 can obtain it need resources. You can see it is in terms of sequence. So no need for you to wait in a middle of a similar simultaneously. So deadlock safe state, still under safe state. System is in safe state if system can allocate resource to each process up to maximum in same order and still avoid the deadlock. Okay, I give a very easy example. Let's say, okay, you have RM 100 today, and you're going to have several like morning, evening, night to spend this 100 ringgit for your food. So let's say in the morning, this morning we call it like process 1, process 2, process 3. Then you need to have this amount of these resources, your resource. So if your resource P1, let's say RM 50, RM 30, RM 20. So you can allocate all. So you can see allocate all your resource to all the process. So it is safe state. If you have one, so you have another safe budget which is RM10. So it is safe state. But let's say you have like here RM50 also. It is not enough supported. So it is not going to be in a safe state. So just a simple example for you to see how and when you're going to have a safe state. If a system in safe state, no deadlock, because no need for you to wait. I need to wait another allowance from my parents. Tomorrow they're going to give me another RM 100, let's say, for me to eat for tomorrow morning, evening, and night. But you can see you need to wait. If you are in a safe state, no need for you to wait. You can occupy all the resources for your all process. If a system in unsafe state, so there is a possibilities of deadlock. So deadlock, unsafe. Sometimes you can see, let's say you have RM 100 just now. So you already occupy RM 30, RM 300. So if there is a possibility, you say, it's already balanced 20 only. You eat 50 for morning, evening 30. Is it there is a possibility for you to get below than that, all this? So there is a possibilities for you to get a deadlock also here, right? Because normally dinner, you're going to eat more, which is much pricey compared to breakfast, compared to lunch. So there will be a possibilities also. But sometimes, okay, then you say, okay, I'm going to just spend for dinner RM10 only. So there will be, it is still unsafe, but there is a possibilities also to have a deadlock. Alhamdulillah, sorry. Okay, so deadlock avoidance algorithm. So you have here avoidance algorithm RAG and bank algorithm similar to the diagram in the beginning slide we looked. All process can be started anytime. When process requests for resource, an avoidance algorithm is executed to check whether deadlock may occur in future or not. So if deadlock may occur, so request is delay. So you're going to delay your request. Let's say P1, P2. So you have only one for resources, which is your in distance only one. If it's already, if it's already belong for P1, so you're going to see there will be a possibilities of deadlock to occur, isn't it? If this P2 request. That's why you're going to have an avoidance algorithm. Okay, don't give any permissions, or if let's say there is a request, it's going to be delay. So when P2 request at a similar time, it's going to be delay this request. Then it's not going to have a deadlock. Deadlock avoidance ensure that system will never enter unsafe state. There will be two, which is first single instance of resources type, which is just now you have like this only, when you have only one instance in your resource. And if you have multiple instances, it depends. You can have at least 2, 3, 4, 5 of your instances in one resource. Normally, this one is going to use in the banker algorithm, and for single will be used a variant of resource allocation graph. Let's take a look one by one, which is our RAG first. And after that, we're going to look into our banker algorithm. These two we can cover easily. So RAG, you need to bear in your mind, although you can see here, you have two algorithms. So this one for a single instances, this one for a multiple instances. For RAG, only single instances in resource. Each process must a priori claim maximum resource use. So you already know the maximum of the P, which is a process. Use variance of resource allocation graph RAG with claim H. So this is the claim H. Last time you have two type of H, which is request, and another one is what? Forgot already. Algorithm. So there is two last time. If you look into the basic, request and assignment H. But now when you go deeper in terms of avoidance, the RAG are using a new type of H, which is we call as a claim H. You try to request. Okay, last time you use it as assignment, but now you're going to you request, but now you're going to see it claim. It try to claim this resource. Indicate that process may request resource RJ represented by dashed line. So this is the illustrations of this statement. Claim H convert to request H when a process requests a resource. So it's going to be convert later on a request H when a process requests a resource. This one is R. So request H convert to assignment H when the process is allocated to the process. So you can see last time you learn request H and you learn on assignment H, but when you have RAG, first of all you're going to have claim H. It's going to be changed to request H when you have a process request resource, and you're going to change to assignment H when resource allocate to the process. When resource is released by process, assignment H reconvert back to claim the claim of your claim H. You're going to reconvert back. Resource must be claimed a priori in the system. A cycle in graph imply that the system is unsafe state. So let's take a look this. P1 now, you can see here, P1 is holding on the resource of R1. Please bear in mind RAG only one, okay, instances, and has claim on R2. At the similar time, it claim R2. For P2, it requesting R1, and it has claim on R2. So here P2 is request of R1 and it has a claim for R2. The differentiation just now is mentioned dash line, and also this one is similar. So the dash line here, you're going to have, this means claim. Similar also for this one, P1 claim R2. So no cycle, because this is on by this and this is request. For here, no cycle. This claim is not yet changed for the first. So no cycle, so system is safe state. So you're going to later on, if it change, if it requests, then it's going to be something else. If it assign, then it's going to be something else. So it's depend on later on of the changing. So the graph was like before continuous. So you can see after this is changed. Before with a claim H. Both right. Before this it is claim. From P2 to R2 is changing now to assignment H. Now it changed assignment H. There is a cycle in the graph which is unsafe. You can see here it's nearly to have a cycle. Just now there is no cycle. Stop here, it will be like this and like this. There is no cycle. Unless you have like this, then it will be cycle. So it is unsafe state. Is stay a deadlock. So supposedly your P2 request R2. Although R2 is currently free because you did not on yet just now, right? It's not on yet by either P1 or P2. It just claim. But now it's on for P2. Is currently free, we cannot allocate it to P2. Since this action will create a cycle in the graph. So this one, because you're going to check. Just now it claimed, right? So you cannot on by P2. It's going to make a cycle. A cycle, as I mentioned, indicate that system is unsafe state. So if, let's say, if P1 request R1, then a deadlock will occur like this, right? So it's going to be having a deadlock. Suppose that P1 requests the RJ. So the request can be granted only if converting the request age to assignment age does not result any formant of cycle of RAG. Otherwise, you're going to only the process must wait and we're going to delay the request. For this, you're going to delay the request. So to avoid the deadlock. So that is on RAG. So I guess it's not too hard. It's quite similar with the earlier example for the age and request age and also assignment age. Now let's take a look another one. This one is much more interesting, which is our banker algorithm. I try to finish the example first. Sorry. So multiple instance in request. So if you have a multiple instance in your resources, then it's going to be under banker algorithm. Similar also, each process must have priority clear maximum use, similar like RAG. When process requests resource, it may wait. When a process get all the resource, it must return them in finite amounts of time. So algorithm could be used in banking system to ensure that bank never allocate its available cash in such a way that it could no longer satisfy the need of customer. So let's see what is the need of customer and how to satisfy. Example in our bank loan. Bank fixed amount of capital for each process. First, no customer will granted a loan exceeding the bank total capital. So if let's say your bank, CIMB let's say. So CIMB have their total capital of RM 100 only. Now it's just having the 100. So if let's say I go to CIMB, can I have a bank loan of RM 101? I just want to have a loan. So can or not? Cannot, because it's already exists their own money, their total capital. So all customer, that is number one. Second, all customer will be given maximum credit limit when opening account. So it is also looking at your background. Not everyone going to have a similar maximum credit limit. If I'm not going to talk about the working, I guess so, but yeah, it is. Okay, let's say you work as a boss and I just a staff. Okay, so of course as you a boss, you have a much higher credit limit if compared to me, because my salary is only like maybe RM 50 per day, but your salary is might be RM 1000 per day. So of course you can support more credit limit. Similar also if you have, I don't know whether you are using a bill or not for your mobile phone, but mine I have I have a maximum credit limit. If I reach more than that, so suddenly it's going to be blocked. Although let's say I pay every month, I pay, let's say my credit limit is 100. So every month I pay and it is okay. It is available. But suddenly I call international maybe. So suddenly at 15 minutes of call is already 101 RM. So it's totally will be blocked my call. It is just because of the credit limit, not because I did not pay my monthly bills, but because of the credit limit. And lastly, the sum of the loan must not exceed of total bank capital also. Okay, about this just now I look into only me, isn't it? But if let's say CIMB, you have don't compare with thousand, with million customer, but we compare only with 2 student. Let's say student A and student B want to have a loan at CIMB. So you have CIMB have similar RM 100, and this student A want to lend RM 60, and this student B want to lend similar amount. It already exceeds also the total capital, so it's not going to give a granted sadly for a second student because it's already achieved the total capital. So that will be applied in a banker algorithm. So example here, how to check whether you are in a safe mode already, safe state. The bank total amount, you have 100,000 and you have 3 customers, C1, C2, C3, and each have the credit limit. So this one is credit limit. How many loan that C1 take? No. Although you have a credit limit. So you can see you have anytime you can try to apply loan. C2 already apply loan. C3 also already apply loan. How many you already have now? 60,000 you already have in the loan. You only have money 100,000. So you can see, oh, you have another 40,000 to support any of these two to make another loans. But you need to check also, this C1 can make a loan, another 40. Okay, let's say C1 suddenly want to make a loan. Can you support? Yes, you can support. Then it's okay. You can see, let's say a C2 also want to have a loan. Yes, you can support. Still, at the available fund. But of course, you can support only one. If this already occupy all, then you cannot give permission to others. But still you want to check whether you are in a safe or not. So you have a available fund which is you can support for all. At least one. So now you can see another example. So this one is safe state. The bank have enough money left to satisfy the customer need, which is on your remaining credit. For example, second example, you have here C1 and C2 try to make a loan of 20,000 and 10,000. So here you can see just now similar, sorry, not similar. Just now is 20, you're going to increase. So you increase is with 1,000, 10,000. Another one, C1 is adding another 20. So although you can see here 20 and 10, you have another available 10K. Supposedly you will say, okay, I set in a safe mode because I have money. If let's say C1 want to have a loan, I can say, okay, you can have a loan, but I have a limit, which is 10K. No, you cannot, because they don't know that you only have this money. They will say, I have another 20. Because you can say, I already lend 20, I have another 20 to lend. So give me another 20. I don't want only 10K. So it is unsafe state. Because you can see here, you cannot support this customer. If let's say at the time, suddenly this customer C want to have a loan, then totally you cannot support also. So it is unsafe state. The bank doesn't have enough money left to satisfy the customer need, which is available fund is less than minimum remaining credit. So that is in terms of the bank algorithm. Later on, in our next class, you're going to see there is several other example, especially when we are dealing with the data structures of a banker algorithm. For now, please understand this theory first on the bank loan for our banker algorithm. So you're going to go deeper in our next class. Is it okay? Any question for this bank algorithm and also our, what else? Another one, RAG. I think this one is quite simple. Later on, when you go deeper also, it's not too hard, especially for Deadlock. I think Deadlock is not too hard subtopic. Until recovery also, it is just on a theory. It's not too hard. Only for later on you're going to see when you want to apply in terms of Deadlock detection, and also for the analysis and the banking also, you're going to have several process to understand. Okay. So if there is no question, we're going to end our class, and I hope that you can join tomorrow's session with our two companies, IIB and forgot another one. So stay safe everyone. Meet you again in our next class on Wednesday. Bye bye.